Hello and welcome to this video. In this video, we will be talking about how to prove divisibility by induction. So let's just start with a simple example. In our proofs, we have four steps. The first step is the basis, as you would. And in the second step, we make a induction hypothesis. And in our third step, we try to use our hypothesis to uh, make the inductive step work. And the final step is the conclusion. But there is a trick with the divisibility rules because the first step is quite simple. You substitute 1 into the formula and you should be able to get a number that proves divisibility. Let's say we've got this function. They usually give you some function and they say, let's say this is, I'm taking a really simple example, and they say, all right, prove that this function generates numbers that are divisible by 13. So what do you do? Obviously, if I substitute 1 in there, it will work. 13 times 1 is divisible by 13. What you do is, let's say, when you make a new inductive hypothesis, you say, all right, 13 times k works. Uh, will it work for, how can I prove that 13 times k plus 1 will work? So the way you would do it is you say, actually, all I have to do is find the difference between the function that has f of k in it and find it. Obviously, the f of k plus 1 generates a larger number. So we actually find the difference between these two. Okay, so all you have to do is find the difference between them and show that the difference between uh, these two functions is divisible by 13. All right, so does it make sense? All right, so show that the difference is divisible by the number that we want to prove. Okay, not the actual f of k plus 1. Okay, because, all right, so the difference is the important part. So let's see an example with this. We are to prove that this function 3 to the power of 2n plus 11 is divisible by 4. So let's start with the basis assumption. With the basis, we substitute 1 into the formula, and with 1 we will get 3 to the power of 2 plus 11. Now 3 to the power of 2 is 9, 9 plus 11 is 20, 20 is obviously divisible by 4. You can write 20 as 4 times 5, and that would prove that it's divisible by 4. So our basis step works, which is great. We tick that off. Now we move on to our assumption step, which has almost no work to do. We just need to write that f of k equals to 3 to the power 2k plus 11 is, we are making this assumption. We don't have to prove it just yet. We're making an assumption that because it worked for n equal to 1, we give it a benefit of the doubt and we assume that it's working, and we want to see and prove that it will work in the inductive step. All right. So the inductive step is where the most of the hard work is done by algebra. So you substitute n equals to k plus 1 wherever the k is. What we end up with is an extra. Notice that this 2 multiplies by both of these terms. 2 is times by k and plus 1. So we end up with an extra factor of 3 square multiplied by 3 to the power of 2k, right? And if you notice, the original equation has only 3 to the power of 2n in it, all right? And this plus 11 doesn't change at all, right? You agree with that? Then what we do is we say, all right, this 9 extra 9, we write it explicitly in front of 3 to the power of 2k. And we are going to do what in this step? We are going to find the difference between f of k plus 1 and the original f of k on the top of the page here. So when we find the difference, what you notice is that the difference is actually just 8 lots of 3 to the power of 2k. The 11 and the 11 cancel away on this line here. So if you take away the terms inside the square brackets, the 11 and 11 cancel away, and we left with 8 lots of 3 to the power of 2k. Now, what's so great about this is that we can write 8 as 4 times 2, okay? And what you can do on this step is to write actually f of k plus 1. Now what we have on the right hand side, in the left hand side, is a negative f of k. And by assumption, that was already divisible by 4, right? So we can add it to the right hand side and write f of k plus 1 like so. When we write the f of k plus 1, by assumption, we know that f of k was already divisible by 4, and this term here has a factor of 4 in front of it, which makes it obvious that is another multiple of 4. So adding two multiples of 4 together will be still a number that is multiple of 4. Therefore, it's divisible by 4. Does it make sense? Okay. So that was our first of 3 examples done. We've got 2 more examples to cover. Okay, you do write a conclusion that involves saying our function worked with n equals to 1, and we made the assumption that it works for f of k, n equals to k, and it also worked for n equals to k plus 1. So in this next example here, we have a function n to the power 3 minus 7n plus 9. And we want to prove that it's divisible by 3 for all integers, positive integers n. So the basis assumption, the basis step is to substitute 1 into the formula. So 1 to the power 3 minus 7 plus 9 makes 10 minus 7, which is a 3. So substituting 1 into the function will give us a 3, which is obviously a multiple of 3 directly. And that's our basis step done. So now we're going to move on to the assumption step. We are assuming that when we substitute k into the formula, it should be divisible by 3, okay? And then we move on to our inductive step. When we substitute k plus 1 into the formula, we have to use our knowledge of binomial expansion here. All right, if you have done pure maths, if you have done chapter 8, what you do to expand this bracket is you write k to the power of 3. The first binomial coefficient is 3 choose 1, which is simply just 3 times k squared times 1. Now multiplying by 1 doesn't change it, but I write it anyway. The next binomial coefficient is 3 choose 2, which is yet another 3 multiplied by k multiplied by 1 squared, which doesn't change anything, but I write it there anyway. And the last term with binomial expansion is 1 to the power of 3. Now there is a 3 choose, you could say there is a 3 choose 0 there as a coefficient right at the beginning, which is a 1. And this last one also has a coefficient of 3 choose 3, which is also 1. So That's just the expansion of that term with the power of 3 there that I've written there. So if I write it a bit neater, what you notice is, and then we multiply the next bracket as well, minus 7k minus 7 plus 9. We're going to put them all on the same line. So I get rid of my handwriting there and put the neater version there. So when we expand the bracket, we had these four terms, and now we are collecting like terms. This 3k minus 7k gives us negative 4k, and 9 and 1 make 10. 10 minus 7 is a 3. So the neater version and simplified version is this bold version, this bold writing. So that's a definition of f of k plus 1. Now we are going to subtract these two from each other, f of k plus 1 and f of k from each other, and let's see what we get algebraically. We are going to subtract these two, and the k to the power of 3 cancels because we have a plus and minus version of it. The 3k square will remain, minus 4k minus a minus 7k will become a 3k, and 3 minus 9 is going to be, oh, all right, so we ended up with this expression. 3 minus 9 is negative 6, and the 3k remained here. This k cube cancelled with this k cube, and obviously minus 4k plus 7k gave us that 3 negative plus 3k. Okay, so these are the terms that match up. Okay, so this is obvious at the minute that we have a common factor of a 3. We can factorize a 3 out of this expression and write it as 3 multiplied by this bracket here. And the last step is to write f of k plus 1 equals to that positive f of k, which by assumption was divisible by 3, and we have another factor of 3 here, or rather multiple of 3. So this shows that we have yet another number that is divisible by 3, right? So we write our conclusion as well. And in our conclusion, we say that the new number is divisible by generated. The new number generated by f of k plus 1 is, we've shown that is divisible by 3. Okay. So this was the second example. Now this last example has a little bit of a challenge in it, which I'll show you. So expect a little bit of extra thinking when you have expression with two powers here. The expressions we have looked at so far only had indices, one index and a constant added and so on, or it was a polynomial. So in this case, we actually have n in two indices. So this is an extra little bit of a challenge there. So we start off our proof by just the basis step. We're going to substitute 1 into this expression, and we are looking for divisibility by 133. So when we substitute 1 into the expression, we will have 11 square plus, let's have a look at it, plus 12. So because 2 times 1 minus 1 is 1. So 11 squared is 121 plus 12. 121 plus 12 is directly 133 itself, which is obviously divisible by 133. So that's our basis step done. We're going to make the assumption that when n equals to k, this expression is already divisible by 133. Okay, so we are giving it a benefit of a doubt. We are not actually proving anything just yet. So in the inductive step, we are going to use this line here, as always. So in our inductive step, we are going to substitute n with k plus 1, right? So when we do that, we end up with this expression. And when you multiply out the indices here, you get 2k plus 2 minus 1 for powers of 12 there. And you will have k plus 2 for indices of 11. So how can we simplify this? Well, let's we need to write it so that we end up with 2k minus 1 for power of 12. All right, so if you look at the original formula there, it has a for 12, the index of 12 is 2n minus 1. So we actually need to turn this into 2k plus 2 minus 1. Okay, so this plus 2 and a minus 1 means that there will be an extra factor of 12 squared multiplied by 12 to the power of 2k minus 1. Do you agree? This is the same as the line above it. And for 11, we had n plus 1, so we just take out a factor of 11 out, and we write 11 to the power of k plus 1. Okay, so what we are going to do then after that is this expression there will need to be subtracted by that very first line that I'm underlining right there. We're going to subtract these two from each other. So let me put it in a neater writing. Okay, so when we subtract these two expressions from each other, all right, so notice that these two blue boxes are the same. So literally, when we subtract them from each other, you're saying I have 11 apples and I'm subtracting 1 apple. So what's 11 minus 1? It's going to give us 10 apples, or rather 10 lots of 11 to the power k plus 1. Now we have, what's 12 square is 144. We have 144 of these blue boxes there, and we're subtracting 1. So 144 minus 1 gives us 143, right? So let's write this, what I just said. We are subtracting these two square brackets from each other. So 11 minus 1 was 10. That's where this 10 came from. And that 144 minus 1, one lot of this, gives us 143. Now, there is still a lot of work, a little bit of work to do. Here's the challenging part, because at the minute, this doesn't look like anything that we can factor 133 out of it. Okay, because 10 is obviously not a multiple of 133. So we are going to split this 143 up. If you think carefully and look at our original expression, we can factor this. We are going to look for a factor of this. So we already have 10 lots of 11 to the power of k plus 1, which is great. So if we split this up into 10 lots of 12 to the power of 2k minus 1, and 10 plus what number adds up to 143? 10 plus 133. Yeah. So when we split this up into, let me write minus 1 here. Let me put the 12 to the power of 2k minus 1 here in a bracket. So what you notice is that we have now, let me write this so it makes more obvious sense. So this term here and this term here are what I've underlined on the very first line, the f of k. So we have 10 lots of f of k, which by assumption was divisible by 133, right? So we have nothing to worry about there. F of k is already divisible by 133, and we have now a factor of 133 that is multiplied by 12 to the power of 2k minus 1. So by this assumption, if I write this a little bit neater, and let me get rid of my writing, we end up with this expression there, which we said is 10 lots of f of k already. And now we can bring, when this is the difference between f of k plus 1 and f of k. So if we add f of k, we will have just 11 f of k on the right side and a factor of 133. So by assumption, f of k was divisible by the number 133, and we have yet another factor of 133 added to a number that was already divisible by 133. So in our conclusion, we write a few lines and say f of 1 was divisible by 133, and the statement held for f of k plus 1 as well. Therefore, it works for all positive integers n. Okay, I hope you found that video helpful, and I will see you in another video.